Hi guys, so we're going to go over complex zeros today. So keep in mind that a complex number is a real number, which I'll label A, plus or minus an imaginary number, which I'll label as B, which is just a number, and then I is to notate that it's imaginary. So it could be plus or minus. One thing to note that an imaginary number, the variable or the letter I, it just represents the square root of -1. So keep in mind that you can't square root a negative. So if you try to square root a negative, it comes out to an imaginary number. So from here, keeping this in mind, let's say I were to square both sides. So whatever I do to one side, I do to the other. So I squared equals to, square and square roots get rid of each other, leaving you with just -1. So note that I have that here as well. I squared equals -1. That's something that you do want to know when we're working with operations of complex zeros. So I have a couple of examples here. Note what's between the parentheses. The most important part of this lesson is to note what's between the parentheses, because depending on the operation is how you combine like terms or multiply or divide like terms. So from here, if I have 3 plus I, and mind you, there's nothing to distribute, so I can remove the parentheses. If there's nothing to distribute in front of the parentheses, I can just get rid of the parentheses, drop down the plus sign, 5 minus 2I. So when I'm adding and subtracting, I can add and subtract by combining like terms. So I have two real numbers. That would be 3 plus 5, which is 8. And then I have two imaginary numbers. So remember, when there's nothing in front of x, there's technically a 1 there. Same thing here with this variable. If there's no coefficient in front of it, that would technically be a 1. So I have 1I minus 2I. So 1 minus 2 is a -1. Drop down its like term, which is just I. And again, we don't really put the 1 in front. So real and imaginary, can't combine them by adding and subtracting. That's your answer. If you look at number 2, the two complex numbers are being multiplied. So you can either distribute or you can FOIL, because when you have two binomials being multiplied together, to get rid of the parentheses and to expand and simplify, you would just FOIL or distribute. So I'm going to do FOILing. So first would be first number in each parentheses. 3 times 6 is 18. Outer would be the 2 on the outside, which is 3 and minus 7i. So that would give me -21i. Inner, I have 5i times 6i, which is plus 30i. And then last, the last in each parentheses is +5 and -7. So +5 times -7 is -35, and it's also I times I, which would give me I squared, because just like when you're multiplying x times x, each one has an exponent of 1, and when we multiply like bases, we add their exponents, giving us x squared. So we're done FOILing, and then once we FOIL, we always look for the like terms, which are here in the middle. They're both with the variable I, so I have -20 plus 30, which gives me +9. Bring down its like term, and then the 18 I'm going to bring down. And remember what we said up here. I squared is equal to -1. So keep that in mind when I have 35I squared, or -35I squared. So I actually have -35 times -1. So I changed the I squared to -1. I'm going to change that to a different color. So I have -35 times I squared, which is -1. -35 times -1 is +35. And then from here, I just have the same problem as the previous. I'm just adding and subtracting, combining like terms. So I have two real numbers, 18 plus 35, which would give me 53, and then drop down the plus 9i. For the next problem, just like when we write a fraction, we can't really have a square root in the denominator because it's just not the way we write it. We usually rationalize and we get rid of that square root in the denominator. It's kind of the same idea when it comes to having a complex number in the denominator. We don't have complex numbers or imaginary numbers in the denominator. So to get rid of it, we multiply it by what's called its conjugate. So conjugates are the same exact term. So 3 and 5i are exactly the same. They're just the opposite operation. So since this is plus, this is going to be minus. But I can't just multiply 3 minus 5i randomly. It's a fraction. I have to keep it balanced. So whatever I do to the denominator of a fraction, I'm going to do the same thing to the numerator of a fraction. And I would say for these type of problems, just take a sidebar and solve each one individually. So we multiply fractions straight across. So for the numerator, I'm just going to multiply by distributing. So 8 times 3 would give me 24. And then 8 times negative 5i would give me negative 40i. Over. So in the denominator, you have the problem just like you had in number 2. You're multiplying two binomials that are complex numbers, and you could FOIL them. But there is a little shortcut when you're FOILing conjugates. And instead of FOIL, you could do what's called Florida, meaning just first and last. If you do FOIL, it'll still work. The outer and inner, though, will add up to 0. So that's why I'm saying the shortcut is just Florida. First is 3 times 3 would be 9. And then last would be 5i, negative 5i. So 5 times negative 5 is negative 25i squared. So I'm just going to take a sidebar here. So I have 9 minus 25i squared. 9 minus 25, again, we know that I squared, notice right there, is negative 1. So we're actually taking 9 plus 25, because negative 25 times negative 1 is positive 25. So 25 plus 9 gives me 34. So what I have here is 24 minus 40i over 34. And you can reduce the fraction here. You can either factor out the GCF in the numerator and then reduce it, or you can put each numerator over 34 and reduce it from there. Either way, it's up to you, but they both work. So for instance, I took 24 over 34 and then took minus 40i over 34, I would reduce each one of these fractions. So 24 over 34, and I'm sorry, I'm writing all over the place. 24 over 34 reduces into 12 over 17, minus, I have 40 over 34, which they're both even numbers, so I'm going to reduce that, and that would give me 20 over 17. So you can leave the answer like this, where you have it split up, or you can combine the numerators together and put it all over 17. Either way will work. And then last, since I wrote all in this section, I just wanted to note that if you're ever given a 0, meaning an x value, and they tell you it's, let's say, 3 plus 5i, just know that when you solve for x and you get a complex 0, the other 0 is always going to be its conjugate, which is 3 minus 5i. So make a note that complex zeros do travel in pairs. They always travel as conjugates. All right, guys, that's everything. Sorry for it being a little messy today, but I hope it all helps.